Hi everyone, I'm Mathieu, this is Yuyou, and today we're going to present you how to define MLIR semantics using an SMT dialect. So let's start maybe with a bit of an example. So we have a simple optimization or simple rewrite transformation in LLVM where we multiply x and y and then we multiply by z. And we want to transform it into we multiply y and z and then we multiply it by x. And the small little problem here is that we have the NSW flag, meaning that if we multiply and there is an overflow, these get transformed to what's called poison, which is cannot undefined behavior. So the question you might want to ask is this transformation correct? Well, the good thing in LLVM is that you don't have to guess. You can pass to external tools like Alive or Alive2, which are automatic tooling. You pass the previous program, the output program, and then Alive2 is going to tell you if it's correct or not. In that case, it's incorrect, and Alive is going to give you an example. For instance, if x is equal to 0, y equal to 100, and z equal to 100, this transformation is incorrect because the first program is going to return you 0, and the second program will have an overflow and returning you poison. So these kind of tools are really useful because they allow you to kind of find bugs in LLVM, and they found like hundreds and thousands of bugs, and also allow to prevent bugs because now that when someone wants to add a new optimization, they can actually check using Alive before actually committing it to LLVM. And of course, if you remove the flag, this is correct because this is just associativity of multiplication. So the question you might want to ask is, can I actually do this in MLIR instead? And so here we would have the multiplication in the arith dialect, and it's the exact same one, and you want to check if it's correct or not. Well, there's other tools as well called MLIR TV, that will do exactly that, exactly the same thing as Alive. You provide the input program, the output program, and it will check if it's correct or not. In that case, it is. But what if you want to use other dialects, your own custom dialects, or for instance, you want to do it for the com dialect in circuit, so com.mo, which has, again, different semantics as the arith dialect. Well, here, MLIR TV is not going to be really happy because it doesn't understand what the com dialect is. This is a dialect that is external of MLIR, so it doesn't understand it, and it's just going to tell you that it's unknown, kind of. So how can we build kind of a more extensible tool? How can we handle an extensible framework as MLIR, which can have external dialects defined by users? In LLVM, this was kind of not easy, but you are in a kind of fixed format. You have just the LLVM operations and nothing else. In MLIR, you might have MLIR that is in tree, but you also have arith, circuits, and all of these different other framework, other compilers that might want to use your tool. So in Alive, you have the way it's designed, you have kind of the infrastructure to do all your proofs, and then you have the LLVM semantics that they find in blue. In MLIR TV, you have kind of the same infrastructure where you have kind of all the handling of all the SMT and everything, and then you have the MLIR in-tree semantics. One way you can think of extending these is to create other tools like Circuit TV or arith TV to do like these kind of proofs for circuit semantics or arith semantics. But the problem you might get is that you start kind of duplicating the infrastructure you have in your translation validation tool. So one other idea you might have is, what if we had all these semantics of like circuit and arith directly in the MLIR TV tool and kind of create a kind of a monorepo of all of these semantics? Well, the problem is that you also have closed source dialects in companies that may want to use your tool, but cannot because they don't want to kind of open their dialects, and also they would have to maintain them in this new monorepo, etc. So this is another problem. So what we're kind of trying to propose here today is, what if instead we have a smaller infrastructure, and then we would plug in our semantics for all our dialects, which is kind of the mathematical meaning. So then we can use these tools on whatever dialect you might want to have if you just provide what their mathematical meaning is, which is the semantics. So for that, let's maybe look at how MLIR TV works. So you start with your input program, your output program. So here, just a division by 8 and a shift right by 3. And then what's happening is that you convert those programs into SMT. So SMT is kind of a mathematical language, or at least a language that has mathematical meaning. So then you can express kind of questions like, oh, for all x, is x divided by 8 equal to x shift right by 3? And then you pass it to an SMT solver, and the SMT solver is going to tell you, yes, this is correct, or no, this is incorrect. But if you're like me, a bit familiar with MLIR, the first thing you might think of is, isn't this just another dialect? Can we just make SMT another dialect? And SMT has kind of a language reference, and the SMT language is a Lisp light language, and those are really easy to translate to a dialect. So that's exactly what we did. We have a kind of one-to-one correspondence between the SMT lib language and our SMT dialect. And that allows us to kind of ask those mathematical questions directly in MLIR. So what's happening now is that if you recall like our previous image, our previous kind of explanation of how MLIR TV works, now the translation from our arith programs to SMT is exactly an MLIR lowering or an MLIR transformation from the arith dialect to the SMT dialect. And if you would have your own dialects, you would just write a lowering to SMT to provide kind of the semantics or the mathematical meaning. And then you would combine those two programs to just check that they're equivalent or not. So with these new lowerings, you can try to provide these new meta tools. So the tool I presented before, for instance, would be a new meta tool using the lowering as an input and using, both the programs and the lowerings as an input. So if we look at what we had before, which is called translation validation, checking that the transformation that happened was correct, you would go from a program to another, you would pass it to the translation validation tool, and it would tell you if it had a miscompilation or not. And how it works in kind of the background is that it just lowered the two programs to SMT dialect, it compares them, and then pass it to the SMT solvers. But since we're in MLIR, we don't actually have to check only that the transformation were correct. What we could do instead is use PDL, which is dialect to represent pattern rewrite. We can use PDL to prove that a rewrite is actually always correct, so that your transformation is always going to be correct, whatever the input programs you have. And the way this is done is that as PDL is a dialect, we can do the same kind of lowering. So for instance, here we have a simple PDL rewrite that's going to check that x plus y equal y plus x. The first thing we do is match two operands, and this translates exactly in SMT by just declaring two constant to integer constant. Then the PDL arith.add operation used the kind of lowering I was explaining before to transform it into an SMT bit vector add, which is just the addition of two integers. And then the operation we rewrite, so the y plus x is going to be handled the same way. And then checking that the replacement is correct is actually just checking that the result of these two addition operations are equivalent, so that they are not distinct. So this is kind of a one-to-one translation we have in PDL, and then we can pass this program into an SMT solver, and it's going to tell us that this is indeed correct, and that this transformation is legal, whatever the input program you have. So in terms of like summary, what we have is that we pass a PDL program, we pass the lowerings of our dialects to SMT, and then we get an answer true or false. And this just is actually a lowering from PDL to SMT dialect, given parameterized by a lowering from all dialects that we're interested in to SMT. And what we decided to do as well is not only looking at rewrites, but also looking at analysis. So now can we check that actually data flow analysis is correct or not for our given semantics? And for that, I'm going to pass it to Yuyou, that's going to present you this.
Thanks, Mathieu. Hi, everyone. I'm Yuyou. I'm from University of Utah. Now, I introduce our project, SMT Assistant Data Flow Analysis in MLIR. Let's look at an example. Suppose we want to add a known-based analysis to MLIR. So currently, MLIR has integer range analysis, has dialect code analysis, but it does not support for known-based analysis. And it is used heavily in LLVM, so we want to have it too in MLIR. So before talking about the details, we can do a quick recap on basic concept. So basically, in the execution time, one bit can have only two possibilities, 0 and 1. However, in the analysis stage, we can have 3 possibilities because we need to reason about all possible executions of our result. So first 2 possibilities is we know that bit is definitely 0 or 1. And the last possibility is we don't have enough information to reason about, so that bit is unknown. Take a concrete example. So suppose we have this known bit for an integer. It has 1, 0, and 2 bits unknown. So in the execution time, it can have 4 possibilities: 1, 3 zeros, and 1, 2, 0, 1, 1, 0, 1, 0, and 1, 0, 1, 1. And in detail, this is how we encode this known bits information. Basically, we encode it as 2 integers, 0 and 1. If that bit is 0, and we set the corresponding bit in known 0 to 1. If that bit is 1, we set the corresponding bit in known 1 to 1. And if that bit is unknown, both corresponding bit in known 0 and known 1s are zeros. Now, we already know how to represent the known bits information. And the other thing we want to know is how to get a new known bits information after applying some operations. Here comes an example. Suppose we have known bits of arg0. Since it's an argument, we have no information, so it's 4 bits unknown. And about C1, it's a constant, so we know all the bits. And we want to know the known bits after applying the arith AND operation. So here comes the concept of transfer functions. Basically, transfer function works on abstract information instead of concrete values. Here, it works on the known bits information, and it returns the unknown bit. More particularly, it has this function signature. It receives the 2 operand, both of them have known bits type, and return a result as a known type. After applying this transfer function, we get a result, and then we attach it on this result. So this is a transfer function. Suppose somehow we implemented the transfer function, maybe talk with our friends or ask her to ChatGPT, and we got this. You can see it performs an OR operation between known zeros and perform an AND operation between known ones. And finally, we combine known 0 and known 1 together to return it. Now, we implement this function. It's natural to compile with 2 questions. The first is it correct or precise? The second is, how should I use it? Let's solve the first question. Is it correct or is it precise? So this is our design. Since we already have the semantics for arith operation, and we can, by giving semantics to transfer functions, we can lower the transfer function in MLIR to SMT dialect. Furthermore, by combining both semantics, and we can lower them to SMT queries and send them to solvers, like these 3, to check correctness or precision. Before that, let's see how LLVM achieves this. So this is a function I took it from LLVM. It's a UTL function used in known bits for calculating addition. And you can see it has the similar shape. It receives 2 known bits argument and return a known bit. And it receives 2 extra argument, it's carrying 0 or carry 1. You can see it contains a lot of operations, such as get a max value, get a mean value, as well as some bitwise manipulation, such as AND or negation. So verifying correctness of this function is hard, because we are working on 2 sets of integers instead of 2 concrete integers. As a result, we also return a set of integers. So this is more hard naturally. And how LLVM test this? This is how LLVM tests this function. First is to specify a concrete bit with 4. And you can see there is a function called for each known bit, for each known bit. Basically, we are enumerating all possible set of integers. And there comes another for each known bit. About the known carry, we're enumerating the carry bit. And inside this loop, and we're still another function called for each number in known bits. So basically, there are 2 level enumeration here. The first level is we are enumerating all possible set of integers. The second level is we are enumerating all possible integer value in that particular set. So this is an exhaustive enumeration. But we can do better, because if we use the SMT version, even on my small laptop, you can verify it in 15 or 16 bits in an acceptable time. Let's see how we achieve this. So this is still the implementation we provided before, and we can directly lower it to SMT. You can see the known bits are lowered to SMT pairs, integers are lowered to SMT bit vectors, the make operation lowered to this pair operation. It's a direct lower transformation. And this is how we check the correctness. Since we already have the known bits, say for 2 operand A and B, we can apply the SMT version of transfer functions and get a known bits result. And here, we also can get 2 instances from 2 known bits and say call them any A or any B. By applying the SMT version of arith semantics, we can get a result. So all we need is to check if the known bits result includes the result. If it is, then our implementation is correct. If not, our tool can give you a counterexample. Now, another tiny thing is precision. Basically, precision means how accurate is our result. We can look at the function on the left. So it's a function receive 1 argument, and it performs a logical shift right on a constant 4. And the shifting amount is specified by the given argument. We can apply known bits analysis on it, say 0, since it's from argument, we have no information, so it's 6 bits unknown. And for the constant 4, we know all the bits. And by applying some transfer functions, it asserts that all bits in A are unknown. It is correct, because unknown includes everything. However, we can do better. So this is another transfer function. By applying this transfer function, we can it asserts that first 3 bits in A are zeros. This is also correct. And you may ask, why bring this example? Because it is a real pull request. Compute known bits, minimum leading or trailing 0 in logic shift right or shift left. So if you want to check the precision of your transfer function, we can also produce a counterexample for you. Now, it comes to the last small question, how to use it. It's easy. Since we already got the transfer functions in MLIR, we can directly lower it to C++, and those functions can be directly used in MLIR dataflow analysis framework. So this is still our implementation. By directly lowering it, we assume that known bits has a type, a tuple of AP ints, and you can see it keeps the same function signature to operand with the type known bits, and it still perform the OR and AND operation on AP ints and return a make tuple. Now, since we already know our code is correctness and maybe hopefully precision, and we also generated C++ code, we can execute the known bits analysis confidently. So we have the analysis on arc0, we have the analysis result on C0 and C1 by applying our transfer functions, and we can get the result of N0 is 4 bit 0 and N1 about 3 bit 0, and thus bits are unknown. And then you might ask another question is, how about the XOR? It's the same. We just provide a new implementation for XOR and check the correctness or precision if you want, and lower to C++, and just execute again. Now, here comes our conclusion. Since we already have this nice empty semantics, and we can do PDL verification on it, we can do translation validation on it, and we can use it in dataflow analysis verification and generating C++ code further. And you can do all other cool stuff if you give in those semantics. By giving those semantics, we can make that happen. Thanks for listening.
So as the person who wrote half the bugs in Circuit, how do you deal with non-binary logic when not X is not equal to X?
Because you have 4-value logic here.
Or 9-value logic, or 3-value logic. Or...
So a small example we have already is like in arith, for instance, we already have a different logic because you have poison maybe. So what we do is instead we store a pair. First we have the value of the integer if it exists, and then we have a Boolean saying, is it poison or not? For something like circuit, I would hope that you can find something a bit similar that has maybe an integer saying, is it, all the possible values you have in your logic kind of. And one thing that you need to change is instead of checking that the actual input and output is equal, you check that it's a refinement. So for instance, that you don't transform poison to a value, but you can transform a poison to a value, but not a value to a poison, for instance.
Thanks.
Hi. Sorry, I'm not very familiar with PDL, but how do you handle loops that you don't know the bound when lowering to SMT?
So that's a research question in itself. And this is something we don't handle for now.
Right.
This is something that would be maybe later on if we can.
Right. Do you have any plans? Do you plan to bound loops or use quantifiers? Or?
At least now we don't have plans, but
Okay.
people have used bounded loops before. In LI, for instance, they use bounded loops to do that.
Okay. Thanks.
So since you eventually can generate like the verified code into C++, have you planned to integrate it not just in MLIR, but wider LLVM projects?
In other, in what, LLVM project?
Yeah, for instance, use it to verify ins combine or something.
So, there's Alive for that kind of, because Alive has made already be able to check a lot of rewrites. But you mean maybe for analysis as well? Or so ins combine is not, so what happens now is when someone wants to change ins combine, usually in LLVM they just add an Alive link that says, oh, we verified in Alive that it's actually correct. So the job in LLVM, I think, is better handled by LI, who's like fitted kind of for LLVM.
I see.
So,
Okay, thank you.
thanks.
Hi. Is there a so? I guess the way to use it is to have a pass that lowers your dialect to SMT dialect, right?
Yeah.
Have you thought about how you would reason about tensors and transformation on tensors, and is that something that's possible?
So that was done. Maybe you know a bit more about MLIR TV, how they handle this.
MLIR TV just load some predefined types and to SMT and some predefined operations, and they're hard to be extended.
So they handle tensors, floating points a bit, but you need a bit of tricks to make it work. So that's
is it something like you explicitly enumerate all the values of tensors? If I do something like constant propagation or constant folding and have an SMT formula for one transformation and an SMT formula that enumerates all the values for on the constant folded value, or
what you need to do is mostly enumerate, probably just enumerate all the sizes the tensor can have.
okay,
The values inside are fine; they can be handled as like kind of constant, and then you can SMT manage to reason about all of them.
Okay.
But I think the sizes is the problem. For instance, integer types needs to be enumerated as well. You need to say it's correct up to 64 bits, for instance.
Okay, thanks.
Thanks.
Sorry, I saw you mentioned Z3, but are you using it because it's integrated in LLVM?
Oh, yeah. We just use these three, but since we're using SMTD, any SMT solver that can handle
You
SMT,
just generate a file and call Z3?
Yeah.
Ah, okay.
So we can also use CDC4, CDC5, and all these tools.
So nice talk, by the way. But typically when I'm writing transfer functions, I like to write them in C++ and not MLIR. So for the verification of data flow analysis, is there a better way to get these transfer functions than writing MLIR? Or is the dialect somehow ergonomic that writing SSA is suitable for implementing transfer functions for, say, 20 or 30 or 50 ops?
I think if you can, maybe I'm not quite answering the question, but so we design the dialect for expressing transfer functions such as APInt, and you write your transfer function in that dialect, and those can be directly lowered to C++, like automatically using APInt.
I was just wondering, like, how ergonomic is it to use this to implement many transfer functions?
Oh, so currently I implemented the non-bits basic bitwise operations as well as for add operation, subtraction, as well as multiplication.
All right, thank you.
Thank you, Mathieu and Yuyou. We'll begin our next talk in 5 minutes.